Okay, so I want to start off by telling you guys what is planned for today and what is planned for the rest of the week. As you guys know, next um, um, next Friday ends the marking period. So we're going to end the 6 weeks before Thanksgiving break. So that means we're going to have a test that's coming up soon. On today, we are going to be talking about projectile motion. Um, on Thursday, we are going to be dealing with the mathematics of free fall, and on Monday and Tuesday. So for you guys, Tuesday of next week, we are going to be having our 6 weeks test. Okay. Now, for the 6 weeks test, on that day, you won't have to log into Zoom. You just basically have to get online and get logged into the system to take the test. And I'm going to remind you guys of that on Thursday as well. But just keep that in mind. You will not have to log into Zoom next Tuesday. Okay. All right. So for today, we're starting a new topic, and that we're kind of getting away from forces a little bit, and we're focusing on specifically on projectile motion. Okay. Now, before I get into projectile motion, there's something I want to remind you guys of. I want to remind you guys of situations in which objects are in free fall. And let's discuss what's happening here, because we're going to need to use these concepts for our topic on today. So everybody knows that if I take an object such as a basketball and I drop it from a building, that object is moving in the vertical direction. It's moving downward in the vertical direction, specifically because the force of gravity is pulling it downward. Okay. And can someone tell me, if we eliminate air resistance, in the absence of air resistance, what is the acceleration of this ball? This was something I told you guys weeks ago. A number to remember. What is the acceleration of this ball? So if y'all remember, the acceleration of this ball is 9.8 meters per second squared. And again, the negative just means it's accelerating in the negative direction. So 9.8 meters per second squared is the acceleration of the ball. So in other words, for every second that this ball is in the air, it increases its velocity by that amount, right? Because that's what that number means. The ball is clearly speeding up as a result of gravity acting on it. So guys, remember that number. Remember, I told you guys, remember that weeks ago. That is the value, that is the magnitude for the acceleration of gravity, 9.8 meters per second squared. Okay. Now, guys, it is important to note that this number holds irrespective of the object's mass. So it doesn't matter if it's a basketball or a bowling ball or whatever it may be, the acceleration of any object falling toward the earth is always 9.8 meters per second squared if we ignore air resistance. Okay. So that is always the vertical acceleration in every situation. Okay. And this is for an object in free fall. But let me ask you a question. What if we're not dealing with an object in free fall? What if we're dealing with let me take that back. What if we're not dealing with an object that is only moving in the vertical direction? What if we're dealing with an object that it's hovering through the air, but is moving in both the vertical and the horizontal direction? That is the focus of what we're going to talk about today. We're going to deal with situations like that, which we call those objects a projectile. If they're being launched and they're hovering in the air or moving through the air, we call that a projectile. So let me share my screen here. Let me show you what I mean by that. Okay, so again, if an object is launched vertically, in the case of this cannonball, it goes straight up and it comes back down. But what and we've already talked about what is the acceleration in this case. The acceleration of the object is 9.8 meters per second squared. But guys, what about this case right here? What if we take an object and we launch it at an angle, something like this? Okay. So if we take our object and we launch it at an angle, what is the vertical acceleration now? Well, it turns out, guys, the vertical acceleration is still 9.8 meters per second squared. In other words, that's the acceleration of the object in the y direction. So, because gravity is the only force acting on it in the y direction, the acceleration of gravity is 9.8 meters per second squared in the y direction. Okay. Now, guys, whenever you launch an object, and this is the important point that you guys need to know about this unit, whenever you are launching an object, and that object is moving in two directions at the same time. So in this case, we saw that this object moved in the horizontal direction as well as the vertical direction. Guys, it is always true that those directions are independent of each other. So in other words, what am I trying to tell you is that whatever forces that are acting in the y direction has no impact on forces acting in the x direction and vice versa. I'm going to say that again because that's an important thing that you guys need to know for this unit. That's very, very important. That the horizontal and the vertical motions are completely independent of each other. In other words, what goes on in x has no impact on what's happening in y, and what goes on y has no impact on what's happening in x. They are completely independent of each other. I'm going to reset this here. So, in this case right here, gravity is acting in the vertical direction, but as the object moves in the horizontal direction, there are no forces acting on it. So what do we know about its motion in the horizontal direction? Okay. Well, in order to present that to you all, let me show you guys this video link here of what I'm trying to say. Okay, guys, notice what I have here on the screen here. So I'm dealing with a cannon, and the cannonball is being launched. But notice it's being launched horizontally, and it's falling off the side of a cliff. Okay. Now, so just like before, we're dealing with a projectile here, where our object is moving in both the horizontal direction as well as moving in the vertical direction. So what's the key point here? Okay. Guys, I want you to notice the two arrows that are shown on the cannonball. Okay. So the arrow pointed downward, that's showing us the velocity of the object in the y direction. Okay. The arrow that's pointed to the right, that shows us the velocity of the object in the x direction. I want you guys to notice something about the difference between the two. The velocity in the y direction, or in other words, the velocity in the vertical direction, notice it increases. Notice how, the moment it's launched, the velocity starts off at 0 at this point. But notice how at the bottom here, we clearly see that the velocity gets larger and larger and larger as the ball falls. And that makes sense because gravity is pushing down on it. Gravity is causing the ball to accelerate in the vertical direction. However, look at the velocity of the object in the horizontal direction, or in other words, in the x direction. If you guys notice, from the moment that the ball is launched, that velocity stays constant. It stays constant at 100 meters per second squared. Well, why does the velocity stays constant? Guys, remember what Newton's first law tells us, that in the absence of any outside forces, an object in motion stays in motion at a constant velocity, in other words, at a constant speed. Okay, and that's what we see here. The moment the cannonball is launched, since there are no forces acting on it in the horizontal direction, again, we're assuming we eliminate air resistance. The velocity of this object in the x direction stays constant. Specifically, it stays constant at 100 meters per second. Remember, just because there's a force of gravity acting in the y direction doesn't mean that the x direction is impacted. Okay, so hopefully that makes sense to you guys. There are no forces acting in the y direction. There are no forces acting in the x direction, and whatever force is acting in the y direction, which is gravity, has no impact on what's happening in the x direction. X and y are completely independent of each other. Okay. With that said, let me ask you guys a question. And before I ask this question, I'm going to give you guys a situation because I want you guys to kind of use your imagination here. Because this independence of x and y, whenever we're talking about projectiles being launched, turns out the physics can give us some very strange results that we may not expect. To demonstrate that, let me give you guys this hypothetical example here. Let me go ahead and share my screen again. So, imagine that that this is me, and I'm standing here. And again, imagine that I have a gun in my hand. Again, guys, just follow my logic real quickly. So this is me. I'm standing here, and I have a gun. So I'm holding a gun. Okay, you guys can see my gun. And I have someone next to me. So there's another individual standing next to me. Let me draw out this person. So this other individual. So this other person here, they are holding a gun. I'm sorry, not a gun, but a bullet. So they have a bullet in their hands. Okay. So I have a gun in my hand, and they're holding a bullet. Okay. Now, let me ask you guys a question here. Imagine for a second that I shot this bullet at the exact. I'm sorry. I shot my gun. At the exact same time that the person dropped this bullet. So let me. Okay. So I shoot my gun, and the bullet goes like this. It's obviously going to fire. It's going to travel a long distance, and eventually it's going to come to the ground because gravity pulls on it. And this person right here, at the exact same time that I fire the gun, he drops his bullet, and the bullet falls vertically. Okay. Let me ask you guys a question. Do you think that this bullet here will hit the ground at the exact same time as this bullet here? Again, I'm assuming, this here is at the same height as this, and this bullet is fired at the exact same time that this bullet is dropped. And again, bullets move very fast, so this is going to travel really far. A lot farther than what I have depicted on screen, but you guys get the point. But at some point, this bullet, is going to eventually hit the ground. My question to you guys is that, do you guys think that by the time this bullet hits the ground right here, do you guys think that that time will match this time right here when this bullet hits this ground all the way on the other side of the field here? What do y'all think? Will those two bullets hit the ground at the same time? A bullet fired at the exact same time that a bullet is dropped. Elijah said no. So, Elijah, I'm glad you said that because that's actually a common response. Most students do say no. Most students say that that one bullet is going to be in the air longer than the other. Okay, but it turns out, Elijah, it turns out that the reality is they both do hit the ground at the exact same time. Okay, I know that seems strange, but it's true that I don't care how far this bullet goes. It's going to travel really far. Assuming this bullet is fired at the exact same time that this bullet is dropped, both bullets will hit the ground at the exact same time. And here's the reason why. Is because, remember what I said, the acceleration of gravity for both objects is always 9.8 meters per second squared. Always. Okay, always. Now, it is true that this object here is moving in both the horizontal and the vertical direction. And it is true that the moment this bullet was fired here, there was a force acting on this bullet in the x direction, as well as another force of gravity acting in the y direction. But remember what I said. Whatever happens in the x direction has no impact on what's happening in the y direction. The two are completely independent of each other. So just because this bullet is moving really fast horizontally, that motion has no impact on what's happening in the vertical direction. Since both this bullet and this bullet here are acting under the influence of gravity, and gravity is 9.8 meters per second squared for both bullets in terms of its acceleration, they both will hit the ground at the exact same time. Now, in case some of you guys don't believe me, there was an episode on Mythbusters where they actually proved this. They actually proved this to be true. And I want to show you guys that Mythbusters video because they actually proved this. That a bullet dropped versus a bullet fired will hit the ground at the exact same time. And let me show y'all this quick video clip.
A real doozy.
Everything's hot, ready to go.
Bullet shot versus bullet dropped. But a malingering magnet is holding up the show.
As soon as it's released, it's just staying there.
But do you think Adam's going to let something like that stand in his way?
Awesome. That works.
Oh, no.
So, the electromagnetic is gone. It's on the scrap heap. We've got a new little solenoid in there which will whoop, get out of the way and let the bullet drop. All we got to do is try it once, get our timings right, confirm them, and we should be ready to do this test.
So the new simultaneous release system is ready for a test fire.
All right, simultaneous release in 3, 2, 1.
All right, let's see how it did on high speed.
But once again, there's a timing problem.
Solenoid's way too slow.
Yep.
It's not letting go.
The most difficult thing about this whole experiment is getting the fired bullet and the dropped bullet to become airborne at exactly the same time. And we can't tolerate even a few milliseconds of variation in this mix to make the result that we want to see happen. It's hard.
Now there's an understatement. So cue the brainstorm.
We're not even seeing the pin start to move.
It gave us the problem that we currently have, which is that it's late.
Having spent the past 4 hours trying to sort out the solenoid,
Look, let's do this twice.
the boys are now staring failure square in the face.
And all it is about figuring out some way to mechanically push between these two.
Until Jamie snatches victory from the jaws of defeat.
You have a hinge that you pull in the middle.
Yeah, that's what I
There
mean.
needs to be some sort of a little bitty catch that is on its edge. If I could make a clip like that.
He adds a small metal clip to the trigger to delay the gun the minuscule milliseconds needed to match the solenoid.
Everything's hot. Let's do it.
And after a few test fires and a bit of fine-tuning, it works.
Bullet leads gun. Oh, it's good. It's good. It's 1/3 of a millisecond difference.
Wow.
That's freaking perfect. Let's go do this full scale.
Okay.
Which means rolling up the room 360 feet to stake out a drop zone.
Right about there. That's where they were landing out in the shooting range, so this is where I expect them to land here.
Okay.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see what it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened. Until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24th of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24th of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
2 bullets, 1 dropped, 1 fired. Amazingly, they ended up in the same place at the same time.
Dude, this myth was every bit as much fun to test as I was hoping it would be. And I gotta say, even though the physics textbooks had it right, I love the fact that we did it full size with real unmodified bullets. I bet no one has ever tried that before.
I think you're right. And whether it was ball bearings or bullets dropped or fired, they all hit the ground at the same time.
Yep. Gravity, man. It's not just a good idea, it's the law. Confirmed.
Confirmed.
The Misters are testing a real doozy.
Everything's hot, ready to go.
All right, guys. So hopefully that video proved to you guys that whenever we're comparing two projectiles, a bullet fired versus a bullet dropped, they will hit the ground at the exact same time. Why? Because remember what I said, the most important thing to remember in this unit. The X and Y components of motion are independent of each other. whatever happening in X has no impact on what's happening in Y and vice versa. Just because the bullet has a certain motion in X, that has no impact on the vertical acceleration in Y, which is 9.8 meters per second squared for both bullets. Okay, so whenever comparing those two projectiles, hopefully that gave you guys an idea of the concepts behind what we're talking about here. Okay, and again, in that Mythbusters video, that few millisecond difference was enough to prove the point within the margins of error, of any experiment. Okay, so now I'm gonna spend like a few minutes with you guys working on sample problems that will look like the problems you will see whenever you guys are working on your assignment later on. So let me pull up this worksheet so you guys can see what I'm talking about. Okay, guys, give me just a second while I upload this into Kami so I can write on it. Okay, so guys, in that video that I just showed you all, in that specific case, we were comparing two projectiles, one bullet that was launched and the other bullet that was dropped vertically. And we was comparing those two projectiles, and we saw that they hit the ground at the same time. Now, in this worksheet right here, we're going to do several examples where we are going to be comparing two projectiles under varying conditions, and we're going to, try to figure out what's going to happen. So we're going to do several of these problems together as a class. And then as we do this, hopefully you guys will be ready and know enough to be able to do your assignment for later on today. Hold on for a second, guys. I just realized that file wasn't completely cleared. Give me just a second. Let me make sure all the annotations are deleted from the previous class. Okay. Okay, guys. Let us start with number one. Again, guys, these are problems that are going to look very similar to the problems these are questions that are going to look very similar to the questions that you're going to see as soon as I make the assignment available in Schoology. But of course, it's going to be multiple choice. Look at number one. So we have two projectiles that are launched, A and B, and A is launched from a higher height than object B. It says which one hits the ground first, guys. This one should be obvious. Remember, in the Mythbusters situation, both projectiles were launched at the same time, so that means they were going they're going to hit the ground at the same time. But here, object A is launched from a higher height than object B. So with that said, guys, which one is going to hit the ground first? What do y'all think, A or B? Come on, y'all. This one should be really easy. This one, in fact, should be common sense. Okay. B is going to hit the ground first because it's launched from a lower height. Okay. Look at number two. In number two, we're launching two projectiles, but we're launching them directly vertically. So if we launch two projectiles at the same speed and we launch them vertically, which one has the greater maximum height? Notice one is 1 kilogram and one is 2 kilograms. Okay. Guys, if you are unsure about what's the right answer, um, um, guys, if you are unsure what the right answer is, I would definitely recommend that you guys use this website here to test the situation. Elijah, it turns out that it's not A. It turns out that both of them eventually reach the same height. And I'm going to show you how you can prove, well, how you can demonstrate that to yourself. So, come to the cannonball, and remember what I said. We're launch. The cannonball is launched, and it goes straight up and comes back down. Let me erase that. So here's what you can do. You can compare situations of different masses. So notice how it says this mass is 1 kilogram and this mass is 2 kilograms. So I'm gonna change the mass here to 1 kilogram. Okay. And I'm gonna launch my ball. Notice how high it goes, and it comes back down. But notice what happens when I change the mass to 2 kilograms. So I'm gonna change the mass to 2 kilograms, and I'm gonna launch it again. What do you notice? It went the same height. I can continue to increase my mass. In fact, I can make my mass 20 kilograms if I want it. If I launch my ball, notice it still goes the same height. So here's the point that I'm getting at. Remember, mass has no impact on the acceleration of gravity. Both these objects accelerate at 9.8 meters per second squared, so that they both slow down at the same rate, come to a stop at the top, and then speed back up at the same rate. So eventually they're going to reach the exact same height because their rate of acceleration is the same. So for this right here, you would say, when it says which has the greater maximum height, you would say that they go the same height. Remember what I said, guys. It's important to keep in mind that mass has no impact on the acceleration of the object. None whatsoever. Mass has no... And again, guys, we're in all of these situations, we're assuming there's no air resistance. We're assuming that there's no air resistance in all of these situations. Again, I want to do a few more just to be sure everybody get the point before I let you guys go and work on these by yourselves. Look at number 3. Number 3 says, for both these objects that are launched, which one has the greatest range? In other words, which one lands the farthest from the table? Now, guys, think about this for a second. You're launching two objects. One object has a velocity of 4 meters per second. The other object has a velocity of 6 meters per second. So which one has the greatest range? Okay. Well, guys, if you're not sure, you can always go back to this link that I'm going to post for you guys in Schoology. And check this out, guys. You can even take this thing right here and you can elevate the height. So you can elevate the height, and then you can make it completely horizontal so that it fires like that. Okay. So guys, I want to compare two speeds. So here it says one is 4 meters per second and the other is 6 meters per second. Okay. Guys, you know what? Let me just compare 14 meters per second and 16 meters per second. See what happens. So this is the object shot at 14 meters per second. This is the object shot at 16 meters per second. Okay. What do you guys notice? Which one went furthest? The one with the greater speed or the one with the lower speed? So it should be obvious that the one with the greater speed went further. So when it says which one has the greatest range, for this one you will put B. Okay. Object B has a greater range. Okay. Let's do some more. I'm kind of skip around here. Let's look at number 13. Number 13 says, out of both these objects launched, which one has the greater vertical displacement? Okay. Guys, remember what vertical displacement means. Vertical displacement just means how far is the object traveling in the y direction. So you're solely focusing on the y direction for vertical displacement. And guys, this should be obvious which one has the greater vertical displacement. Notice ball A, before it hits the ground, it's going to go a total of 2 meters in the y direction. But object B, before it hits the ground, it's going to go to a total of 1.5 meters in the y direction. So just by looking at this diagram here, it should be obvious to you all that A is going to have the greater vertical displacement. In other words, A is going to travel the greatest distance in the y direction. And you know that just by looking at it. Here, this is 2 meters from here to here. Here, this is 1.5 meters from here to here. Again, let us do some more. Okay, I'm gonna turn on the back. I want to do some on the back here. See, guys. Let us look at number 20. Number 20 says, which one hits the ground first? So let us compare object A and object B. Okay. Notice both objects are launched with the exact same initial speeds. Okay. The only difference is the mass. Okay. But guys, remember what I said before. Mass has no impact on the acceleration of gravity. Since these objects are both launched from the same height and they have the exact same acceleration, it should be obvious to you all that they're going to hit the ground at the same time. Okay. So when it says which one hits the ground first, you will put they will hit the ground at the exact same time. Okay. And of course, guys, if you're unsure of that, whenever you're answering these questions, just go to this website and kind of test it. So test two situations here. So you want to keep the speed the same, but you want to change the mass. Notice here, if my speed is 16 meters per second and I launch it, my object travels like this and it hits the ground. If I change the mass, okay, and assuming you had a stopwatch and you could clock that, you would notice that in both situations, they're going to hit the ground at the same time because the acceleration of gravity is the same for both of them. Okay. Let's look at some more. Let us look at number 22. Number 22 says, which one is in the air for less time? Okay. Now, guys, it should be obvious to you all that if we're still looking at the y direction, the object that has the object that is released from the smaller height should have less time in free fall. So since B is launched from a lower height than A, we would say B is in the air for less time. Guys, someone in my last class asked me about number 23 because 23 looks kind of complicated because here, they give you the velocities of the objects in both X and Y. But notice what the question says. It says, which one of these has the greatest vertical acceleration at the top of its path? Okay. But guys, I'm going to tell you guys right now, on your homework, whenever you see something like this, and it asks for vertical acceleration, guys, I'm going to tell you guys something that I just need for you guys to remember. The vertical acceleration for all objects falling toward the Earth is always 9.8 meters per second squared. Okay. So both A and B will always have an acceleration of 9.8 meters per second squared at every point during their path of motion for both, and that's true for both objects A and B. I don't care what the mass is. I don't care what the initial velocities are. the acceleration, the vertical acceleration is 9.8 meters per second squared. And again, we are assuming that we are knowing air resistance in these examples. So since both objects have a vertical acceleration of 9.8 meters per second squared, you would say that the vertical accelerations are the same for both A and B for 23. And guys, that is true. That is true for every single situation where we are dealing with vertical acceleration. Okay. Let us move on to you know what? I want to do number 29 because number 29 is a good one. On number 29, it asks you to compare 3 different situations here. Notice how we have 3 objects launched from 3 different angles. Well, hold on, guys. You know what? You know what I want to do, guys? I want to do number. Okay, hold on. We're gonna come back to number 29. I want to do number 18 before I do number 29. Because number 29 asks about see, number 29 is asking about the maximum height, but here I want to focus on the vertical range first. Okay, so we're going to come back to 29, but let me look at number 18 first. Okay. So guys, look at number 18. If we have 3 objects that are launched, A, B, and C, A, B, and C. One is launched from 45 degrees, one is launched from 60 degrees, one is launched from 30 degrees. Which one of these has the greater range? Okay. And again, they're launched with the exact same initial speeds. Guys, if you don't know, just go to this right here, this website, and test it. Okay. Remember, guys, we're launching from the ground, so I'm going to kind of lower the height of my cannon. Okay. Okay, so guys, I'm going to start with 45 degrees first. Okay. So let me change my speed a little bit. Okay. So guys, I'm going to start with 45 degrees. Okay. Okay, guys, if when my angle here is 45 degrees, okay, and when I launch it, okay, I want you to notice how far the object travels. Okay. Now, let us switch our angle to 60 degrees. So I'm going to switch my angle to 60 degrees. And then I'm going to launch it. Okay. And, okay, now notice how far I traveled there. Now, lastly, I'm going to fix my angle. I'm going to change my angle to 30 degrees, and let's see how far it travels. So change this angle here to 30 degrees. And then I'm going to launch it. Notice how far it travels. Okay. So, guys, out of those 3 scenarios, which one went the furthest? Okay. Hopefully, it should be obvious to you that the one that was launched at 45 degrees went the furthest. So, situation A has the greater range. Guys, as a general rule, and this is something I want you guys to remember for the test, that 45 degrees is always going to be your sweet spot whenever you're concerning yourself with range. So whatever angle you launch from, you can launch from 89 degrees, or you can launch from 66 degrees, or you can launch from 32 degrees, 24 degrees. Any of those angles don't compare to the 45 degree angle sweet spot. 45 degrees will always give you the longest range. Okay. Now, let us look at number 29. So, we're still dealing with the situation where we're launching 3 projectiles, but now it's asking which one has the greater height. Okay, well, guys, if you go back to this, it should be obvious which one of these has the greatest height, and that is the one that was launched at 60 degrees, right? So if we launch our object at 60 degrees, that one gave us our greatest height compared to 45 degrees and 30 degrees. So for this one, our answer here is going to be object B. It's going to give us our greatest height. Okay. Okay, so guys, hopefully you guys have enough to do the assignment for later on today, enough information to be able to work through this. Just remember what I said, that the important things you guys need to remember. The important things you guys need to remember from today is that the horizontal and the vertical motions are completely independent of each other. What's happening in X has no impact on what's happening in Y, and vice versa. Okay. Another thing you guys need to remember is that the acceleration of gravity in the Y direction is always 9.8 meters per second squared, and it does not matter. It does not matter. Does not matter what the mass is, the object's acceleration will always be 9.8 meters per second squared. And guys, one more thing. If the problem asks you, if you have a projectile that's launched, and the problem asks you what is the vertical velocity at the very top of its path, that should also be easy. Guys, if you notice, the velocity of the object at the very top is going to be 0. And that makes sense because the cannonball is launched, it goes all the way up, then it comes to a stop before it comes back down. So the vertical velocity will be 0. Okay. The vertical acceleration is always 9.8, but in this case, the vertical velocity at the very top is 0 because it slows down, comes to a stop, and it speeds back up. Okay. Any questions before I let you guys go? Any questions?